I now call to order the Society's 2,380th meeting in the 146th year since its founding in 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I'm the president of PSW, the oldest scientific society of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Jim Garvin. Tonight is the Society's annual meeting. We are ever mindful of the words of founder and first president Joseph Henry that the Society should devote as much time as possible to the discussion of scientific matters. He sought to avoid, as he put it, the bane of many societies, the time consumed in details of business and in the discussion of non-essential points. He insisted that the Society obviate this evil and put it, as he put it, and secure the devotion of almost every evening exclusively to the scientific purposes of the Society. Tonight we'll justify his use of the qualifier almost every evening to meet the modest requirements of the Society's bylaws to hold a meeting annually on the first meeting of the fiscal year, and at that meeting to communicate to the membership the President's report on the state of the Society for the fiscal year, in this case the one ended June 30th, 2017, a report on finances and membership, and the report of the Audit Committee. I will summarize these, and if you want to have the full report, please see corresponding Secretary Robin Taylor. Where are you, Robin? There she is, raising her hand. And she will get you copies of the full reports. I am pleased to support that the Society did well. There, just so we know where we are. The Society did well in the fiscal year ending June 30th, 2017. Programs were, by all accounts, well received, and in at least some cases, among the very best offerings on science in the area. The lecture by David Kaplan, which was preceded by a showing of his film, Particle Fever, and the Henry Lecture by 5 speakers on exoplanets were particular highlights. Lecture attendance grew slightly over last year, averaging over 100 per lecture. Attendance at the pre-lecture dinners has continued to be strong, averaging about 25 for non-formal events and about 50 for formal events. Total and dues paid membership both increased again this year, continuing an upward trend that started a few years ago. The Society's finances are strong. Dues and contributions grew over the last year, and sponsorships almost doubled. The Society now has adequate financial reserves and sufficient funds to consider expanding its programs to 18 or 20 lectures next year. The Audit Committee reviewed the Society's accounts, found them sound without material issues that need to be addressed. I'm pleased to report that at long last, the new website is well on its way to a launch this fall. The Society purchased equipment to stream lectures this year, and we will be streaming tonight's lectures to beta testers. Fingers crossed. As mentioned above, detailed written reports will be available. Just let corresponding Secretary Robin Taylor know if you would like to have a copy. And after the lecture, if you have any questions on this, you can ask me. So, we're back to our lecture. We now turn to our program for the evening, which will begin with a few announcements, followed by a reading of the minutes of the 2,379th meeting. Because of the time taken by the annual meeting report I just gave, we will forego recounting an historical meeting from the PSW bulletin, but we will resume doing that next meeting. After the minutes, we will turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and adjourn the meeting to the social hour. Please join me in thanking the sponsors of the Fall 2017 and Spring 2018 lecture series, this Policy Studies organization in cooperation with the American Public University, and a generous sponsor who has asked again to remain anonymous. I am pleased to announce that the following new members have been elected to the Society. James von Artstelen, a computer scientist with Securicon, LLC, interested in geology, physics, and cosmology, and first daughter to be interested in presentations by NASA scientists. He learned a PSW through Washington Post Skywatch. Jared McQueen, an engineer with cybersecurity innovations, interested in a wide range of subjects, from systems engineering to astrophysics. Jared is helping get PSW's new website up and running, and he is running our streaming tonight. Eleanor Doherty, an educational consultant interested in research on learning and in population research. She learned a PSW through a friend. Shamila Mohanraj, a physician at Georgetown University Hospital interested in infectious diseases, particularly HIV, who found PSW on the web. Gail T. Chinnery, a physicist and engineer, retired from EPA, interested in particle physics, astrophysics, and origin of life studies, who learned a PSW through the Geological Society that actually meets in this room. And tonight's speaker, Jim Garvin, whose interest will be obvious from tonight's proceedings. Please join me in welcoming them to the Society. Now, I would ordinarily say, if any of our new members are here tonight and would like to pick up their signed reprint of Volume 1 of the PSW Bulletin, they should come and see me. But unfortunately, your president, esteemed as he may be, forgot to bring them. So I am terribly sorry and apologize to those new members. But I will remember next time, and you can pick up your signed copy of Volume 1 of PSW Bulletin, which is interesting because it explains why those folks back in the 1870s decided to name the organization the Philosophical Society of Washington. And you might understand why we are insisting on calling it PSW. Okay, I'll tell you why. Because back then, philosophical meant essentially natural philosophy and the study of nature. And it was really the term for science. And these days you say philosophy and people want to talk about Hegel and Kant and issues of theology and teleology. And that's really not what we do very much here, although when we go across the street to the bar and things get late and we start wondering about final purposes, maybe we do. But our lectures are technology and science. So there are a couple of changes to the General Committee that are well worth noting. First, to our great dismay, Recording Secretary Preston Thomas has moved to Phoenix and has had to resign because of that. Now, we will miss Preston terribly, but fortunately, Membership Chair James Heelan has agreed to take over from Preston, and his appointment as Recording Secretary has been approved by the General Committee at the summer business meeting. So please welcome James to his new role as Recording Secretary. Finally, we have a new addition to the General Committee, Social Media Director Ann McQueen. Ann's appointment also was approved by the General Committee at the summer business meeting, and she will be tweeting to all of us. So please welcome Ann. And to get things started on the right foot, Recording Secretary James Heelan will now read the minutes of the last meeting on exoplanets.
To be clear, these are Preston Thomas's final minutes, and I'm just reading them on his behalf. At the Cosmos Club in Washington, D.C., on May 12, 2017, President Larry Milstein called the 2,379th meeting of the Society to order at 7:50 p.m. This was the 86th Joseph Henry Lecture, named in honor of the Society's first and longest-serving president. President Milstein announced the order of business and welcomed new members. The minutes of the previous meeting were read and approved. President Milstein then introduced the four speakers for the evening: Deborah Fisher, Hannah Wakeford, Sean Domagal Goldman, and Aki Roberge, along with moderator Mark Clampin. The lecture was titled Exoplanets and the Search for Life, an Exploration in 4 Lectures. Dr. Fisher's lecture was titled A Universe of Exoplanets, She presented the famous pale blue dot picture from the Voyager spacecraft and explained that the goal of the exoplanet research is to get a picture of other exoplanets as good as that pixel. Dr. Fisher described how her team uses the Doppler shift of light from distant stars to deduce the presence of exoplanets that we cannot yet resolve with existing telescopes. Although planets orbit stars, stars themselves also move slightly, orbiting the center of mass defined by the star-planet system. This motion of the star subtly shifts the spectrum of light coming from it and the absorption lines from within that spectrum. The magnitude of this deflection can hint at the mass of orbiting planets. Dr. Fisher also described the transit technique of detecting distant planets. By measuring the brightness of a star and noting recurring dips in the brightness of the star, we can deduce the radius of orbiting planets that pass in front of it, which provide their volume. Together, the Doppler and transit techniques can provide the density of the planet to further discern whether it is a gas giant or small rocky planet of the type that we think may support life. Dr. Fisher concluded by explaining that the next step for her research is the deployment of the EXPRESS, Extreme Precision Spectrometer, with the goal of further refining the Doppler method to sensitivities of 10 centimeters per second, which is enough to detect gravitational disturbances by planets the size of Earth. Next, Dr. Hannah Wakeford discussed exploring the TRAPPIST system with Hubble and the James Webb Space Telescope, or JWST. She explained that each element has a unique spectral fingerprint, so that when light from distant stars passes through the atmosphere of a star transiting exoplanet, not only is the planet detectable, but its atmosphere tints the starlight. Measurements from the Hubble can detect this tint and provide an estimate of the atmospheric composition of the exoplanet. Large gas giants are easier to analyze with this method because there is more atmosphere and thus a larger signature. To analyze smaller, rocky exoplanets requires finding planets orbiting colder, redder stars, which make the small planets easier to notice. The TRAPPIST-1 system provides a superb example of such an arrangement, with a nearby ultra-cool M-dwarf star orbited by 7 rocky planets. Dr. Wakefield concluded by noting that the TRAPPIST-1 observations from the JWST will provide us the first solid data to speculate on how easily solar systems and planets like our own form, and what sort of environments we can expect on those planets. Next, Sean Donegal-Goldman described the search for life on exoplanets. Dr. Donegal-Goldman contrasted the ease of finding signs of life on Mars and in Earth's fossil record with the difficulty of eliminating the false positives, of which there have been many. Spectral analysis is also prone to false positives, in which telltale elements such as oxygen, methane, or even water can exist on a planet that is nonetheless not conducive to life. The ratio of these gases is key, because life provides a source of oxygen and methane to replenish them and maintain them in an otherwise untenable balance. Discovery of a planet maintaining a high concentration of oxygen in the presence of methane would be, he explained, cause for champagne. Finally, Dr. Aki Roberge described Finding Earth 2.0, extraordinary tools to expand the search space. She emphasized the need to be able to image planets directly, rather than mixed with star photons as occurs in the transit method. Of course, even nearby stars are so distant that the planets orbiting them will be nearly swallowed up in the star's glare, making direct imaging very difficult. One answer to this need is coronagraphs, which block out the sun to make nearby planets visible. Internal coronagraphs already exist, which can modify the stream of light entering the telescope. More ambitious, star-shade satellites would attempt to block the light entering space telescopes. Such vehicles would be extraordinarily difficult to build, position, and maintain, but could deliver equally extraordinary imaging capabilities. The forthcoming W-FIRST 2.4-meter telescope is comparable in size to the Hubble and will include a technology demonstrator of a coronagraph and deformable mirror. It may also be paired with an experimental starshade later in its life. Ultimately, however, the W-FIRST's lens will be too small to directly image exoplanets. The true successor to Hubble will be the Large UV Optical Infrared Surveyor, LUVOIR, an 8 to 16 meter aperture, multi-spectrum, upgradable science platform capable of spectroscopically surveying small habitable zone planets around a range of stars, including sun-like stars. Dr. Roberge explained that the telescopes now on the drawing board provide us a very real prospect of finding and describing the first Earth-like exoplanets. After the conclusion of the talks, President Milstein invited questions from the audience. In response to a question about detecting other life-friendly attributes, such as moons, Dr. Roberge and Dr. Fisher noted that our theories on what factors are conducive to life are woefully short on data and have routinely been invalidated by new observations. As Dr. Wakeford put it, our imagination is not as good as nature's imagination. Another questioner asked the panelists to share what for them would be a definitive indicator of life. Dr. Domagal Goldman reiterated that oxygen and methane coexisting together would be a clear watershed. Dr. Roberge emphasized the need for a holistic measure of all the elements present on a planet, enough to support a strong model of their generation and sink rates. The reliable indicator of life would be an anomaly in these ratios that is not attributable to simple physical or chemical processes. A final questioner asked the panel to describe their reasons for search for life beyond Earth. Dr. Wakeford and Dr. Clampin explained that the pursuit of one of mankind's questions is a powerful inspiration that attracts new generations into STEM and pushes scientific inquiry and engineering achievement forward. Dr. Roberge added that if humanity is not to end when Earth does, we need to already be looking for new homes. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:04 p.m., President Milstein adjourned the 2,379th meeting of the society to the social hour. Temperature, 10 C. Weather, light rain. Attendance, 139. James Heelan, new recording secretary, on behalf of Preston Thomas, former recording secretary.
Thank you so much, James. It's one of the jobs that takes the most work. Are there any corrections to the minutes? Additions, subtractions, notations? If not, I will entertain a motion from a member to approve the minutes. That would be, no kidding, really? Another, I have a second. Second, Carrie seconds. All members in favor say aye. Aye. All members opposed say nay. Minutes are unanimously accepted and will be posted to the website by our web person in due course. We now turn to tonight's lecture on the exploration of icy ocean worlds and the search there for signs of life. It's my pleasure to introduce tonight's speaker, Jim Garvin. Jim is chief scientist at NASA Goddard Space Flight Center and co-chair for the Europa Lander Science Definition Team. He's been with NASA for 32 years, serving as NASA chief scientist, as chief scientist for Mars exploration, and as project scientist for the Earth Systems Science Pathfinder program, among other roles. Jim was a leader in developing the strategies and implementation of the Mars exploration rovers, the Mars Reconnaissance Orbiter, the Phoenix Polar Lander, and the Mars Science Laboratory Curiosity. He's provided critical leadership to many other programs, too numerous to mention here. Among other awards, Jim is the recipient of 2 NASA Outstanding Leadership Medals and 2 Presidential Rank Awards. He has published over 90 technical papers and popular articles, made numerous presentations to scientific and lay audiences, and appeared frequently on television, speaking on space exploration, including appearances on Letterman and Alien Planet. Jim earned a BS from Brown, an MS in Computer Sciences from Stanford, an MS in Planetary Geology from Brown, and a PhD in Geological Sciences from Brown, where he's been celebrated with the Rogers Award for outstanding contributions to science. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Jim, who has already come to the podium.
Thanks, Larry. Let me grab this. There we go. Well, thank you. Can everyone hear me? I'm just going to hope that this thing connects, and we'll be good to go. There we go. It's thinking. Sorry. It's probably against Europa already. So what I'd like to do today, assuming the slides eventually...
Are you good? Wait, are we good back there?
It's still thinking. Whoop, maybe I have to force it.
No,
Hang on.
wait, don't do anything.
Don't do anything. They're trying to stream it. So what I'm going to do tonight is try to paint a picture.
Wait. We can't stream it if you
Oh,
don't
okay.
hear you.
Whoops.
So you're good. So he sees what you see. So now you got to get your.
Okay.
I don't know why you're not. You're
Yeah.
just seeing a blue.
All right, I'll try. Sorry about this, guys. It worked before, but, you know, we'll try this. Maybe this does it. Maybe it needs to be, oh, there we go. Well, it is recovering my document. Okay, that's good to know. There we go. Okay, there we go.
Give it a moment.
Give it a moment. Sorry,
Patience,
folks.
patience in all things.
All right, there we go. Whoa, jeez, whoop, good. Slides work. All right, thanks,
You good?
Larry.
All right.
We good? So today, folks, I want to take you on I hope, a journey of the mind in the quest, what we would say is the search for signs of life in a little different approach. You heard from the astrophysicists a couple months ago. We've, of course, been at this search ever since we awakened as people. I'm going to change the search a little, borrowing from some great discoveries by Galileo. We celebrate him for a long period of time. And remembering, in fact, the legacy of a mission called Cassini that recently ended after the vision of flying that to the Saturn system. And I remind you that we're coming up on the 30th anniversary of the grand tour of the mission known as Voyager. And I don't know how many of you saw the Washington Post or the New York Times, but when that mission first completed its tour, and the vice president at that time spoke, they had a nice little panel that had Columbus, Magellan, and Voyager as the great discoverers of that period in time. That was the late 80s. So I want to take you the next step, where we think we can learn more, and that next step may be to worlds that we think are bigger ocean worlds than our own. And think of that. We live on an ocean planet. I like to tell the kids, misnamed Earth. I personally am a geologist and dearly love that rocky record, but the ocean story is the important one, and finding other worlds where the oceans work differently may offer hopes, prospects, scientific opportunities to search for life. So let's think about what Galileo gave us. There's Galileo's data. Inspiring, he apparently was a great artist. This is Jupiter, where our Juno spacecraft is now orbiting. And these are the Galilean satellites. Of course, he didn't name them for himself. And it turned out that he only knew they were big, probably at the scale of our own natural satellite, the Moon. So Galileo kind of got us started in this quest to ask, you know, are we alone in our little tiny solar system, ordinary or not, important or not? Are we alone because we find other things at the scales that we already know? And so, flash forwards 500 years, the Voyager spacecraft and then the Galileo spacecraft entered the Jovian system, and almost large enough to be a mini secondary star system in our little solar system, and discovered the cue ball planet. Now, I don't know how many of you were watching what Voyager did in 79 and 80 when it made its first flybys of the Jovian system, but I can just describe for you the leaders in planetary sciences being at a loss of words as they saw Io and Europa and Ganymede and Callisto and wondering, what were these things telling us? This cue ball planet, the size of our moon, the land area here, the size of Africa. How many here have walked across Africa? Okay, so one, good, and Mark two. So it's a long way. I walked a few hundred miles in Australia. That was hard enough on my shoes. So here we have a world that big where we now have reason to believe there is a subsurface ocean at the scale that we never would have believed. In fact, volumetrically, it's bigger than that we have on Earth. For our ocean planet, we think of our ocean as being, everywhere, but really its average depth is 2.7 kilometers. That's pretty deep. How many of you scuba divers go to 2.7? Hopefully none. The pressure alone would be rather challenging. But here's this little world, the size of our moon. This is Europa. This is Earth unloaded from its oceans today. And we have an ocean bigger than that of our own, protected from the space environment, which is really not too conducive to life. We also have reason to believe that this cue ball planet, because of its shape and appearance, is a very dynamic world. It's difficult to maintain those appearances at those scales without something leaking, without some dynamic. And while it took us, humans, 1,000 years to realize we were living on an eggshell planet, plates grinding along, and if you want to see them in action, visit Iceland. And how many of you have been to Thingvellir and seen the two-plate? Great. So go visit. It's great to see. They're moving. Well, it's moving here. We now have reason to believe that the crust of Europa may be deforming 100 feet every orbit of the satellite. 100 feet. Imagine that at the scale of this building or something else. That's a potential possibility due to the access of this world to this ocean. This is one of our best pictures of Europa, showing an area of chaos. We have names for these things, originally devised to describe the fact that we really don't know what they are, but they do provide us with an opportunity to study. So we believe this planetoid, the second of the big Galilean satellites, harbors an ocean that exchanges with its space environment, its exosphere, producing signatures perhaps, and exchanging the oceanic waters, gases and molecules as deposits on the surface that we think we see in some of the best pictures from Galileo. But there's a problem. Europa lives in an environment that's not really that which we would enjoy as living things. It lives in the radiation belts of an almost big enough to be a star planet known as Jupiter. And the radiation environment there would fry eggs, literally, sort of figuratively. But anyway, would not be conducive to the long chain organic molecules that we're all made of. So this little world, if it's going to be a place where we search for signs of life, has to protect that life. So we have built a theoretical model of how Europa might work. Now, we don't know all of this. This is our best working hypothesis from the observations of Galileo and Voyager and work since then by many institutions. But the idea of a large 100-kilometer thick, deep ocean, perhaps salty, perhaps acidified in the upper regions, interacting with a silicate ice shell that at places could be as thin as a few miles, like the thinnest oceanic crust on Earth. For those of you who have been to Iceland and went to the Blue Lagoon, you know, there's hot rock under you, not far, and it erupts a lot. So this could be happening there, only it's not hot rock. It could be the bubbling waters of this large engine potential for life. And in astrobiology over the last 20 years, we've come a long way, baby. We've come from things in rocks that we didn't know what they were, but might be signs of life, meteorites we think are from Mars, to asking questions about oceans around nearby worlds. Now, Europa offers another thing. Now, this, of course, is Hollywood's view of the beach ball Europa. So this is a footprint for scale. But the environments that we can imagineer at the surface of Europa don't follow our textbooks. We have ice and silicate rocks at different temperatures and pressures than we're used to here on Earth. They don't work the same way. And that's why science is so fun when we think about how would we study this world? How would we go? We've flown by now twice with Voyagers and then with Galileo. So the kinds of terrains we would see at the scale you would land on and walk on are not going to be those that you would go into doing field biology or geology. And this is the kind of surface at a scale of tens of miles by 100 that you would imagine on Europa. Blocky, plate-like features, only hundreds of meters high, suggesting a dynamic that we don't see really anywhere else but Earth. So about a year and a half ago, commissioned by NASA, help from the National Academy, the idea of what would be the next step in Europa exploration beyond reconnaissance was put forth as a study of myself and Kevin Hand from the Jet Propulsion Lab and Allison Murray from Desert Research Institute, co-chaired a team of 21 scientists, women and men, experts in the potential biology of environments that are chemically and energy challenging and yet which on Earth life survives. How many of you know about life in Lake Vostok? Probably some of you. Great. Okay. So who would have thought if you were in the 70s that was the case? So the vision we have is not of a murky, almost stealthy lander, but of sending an analytical laboratory to Europa, handling the environmental conditions and doing the kind of work that we first set off to do a generation ago with the Viking mission to Mars. So let me step back for a minute now and set the stage. And you heard from people like Mark and others in the search for signs of life astrophysically, beautifully captured here. And maybe one of our missions in space is asking this question. Of course, I would put it back to you. What is it? What do we mean by being alone? I mean, alone is a state of mind, maybe philosophical, hence appropriate here. Some people are perfectly not alone reading their books, talking to trees, whatever you like. But that is an important question we've all wondered about. Today I'm going to talk about going not astrophysically out, although that's critical, but starting at a new place to look. a challenging place where the technology and science and engineering get together and try to crack that problem and open up ocean worlds to science. Now, as a NASA person who worked at headquarters, I'm required to show the wiring diagram of how we think. So please forgive me for a minute and just remind you that the big questions we ask are all connected through the places we study this universe from space. And that starts at Earth, our working natural laboratory, our spacecraft, swirling through space rather faster than a speeding bullet, connects to that astrophysical domain that we see and sense remotely, and comes back to us as we ask things about the neighboring accessible planetary worlds. And those connectivities are cross-disciplinary. It's not just about biology or chemistry or physics or the record in the rocks. It's about reading those records in ways that allow us to basically address these three big questions that our current associate administrator has been putting forth. We are looking for the fundamental physics and chemistry of the universe, such as telescopes at James Webb. We're searching for those signs of what we might define as life elsewhere, while we're safeguarding and looking at our own survival on a planet as living things. But the connectivity between those, not just with missions, is with how we do our work. So today I'm going to talk to you about that simple paradigm of looking to characterize, to enable us to build understandable models and then actually have predictive capability. So the first new revolution I remind you of is that biology has not been quiet over the last 30 years. And some of you biologists will stand up and tell me you're much stronger than I can. I'm a rock guy. But we now even have a ladder of life. I mean, you know, before we had a basket of rocks, now we have a ladder of life. Well, that was a joke, folks. It's after dinner. And the ladder of life defines a set of questions we would ask about things that we would believe are life in the viewpoint we have here on Earth, self-replicating biology, chemistry, physics, and we have a context today. One context is, since 1980, and it's embarrassing to state this, the leaders of science in this country have said we want rocks back from Mars to finally put that beast to rest, because she's a big planet and confusing, we need them back. And secondly, we need to extend our laboratory presence, not just remote sensing-wise, but to physical laboratory measurements there before we can bring them back, and hence what I'm going to talk about today. So some of these paradigms, looking at just the basic building blocks, the signatures of the amino acids and their handedness, antennometric excesses, all the way up through the scale of things we could detect, are what we're up against. And we've been to this party, folks. Now, a lot of you are young, but when I was in undergrad, we sent a mission to Mars called Viking. We went in asking, can we see dynamic microbial life metabolizing and producing signatures that we can detect? And Viking went to Mars, read the environments, and found that they were challenging. They're radiation dosed at levels we weren't expecting. Superoxidants were detected. The chemistry was more reducing. Lots of things that led us to no definitive positive in the chemistry of that environment. Just remember, folks, we had never sent a gas chromatograph mass spectrometer instrument ever off planet. We had to send it to Mars the first time. They worked perfectly. We landed 0.5 metric ton of labs on Mars, and we came away with Mars as a sterile, polar, cold desert with its fun stuff way in the past. And so the past is good, but the past sometimes is boring. And so we redefined Mars to look for life inference in the records of what might be a place that could be habitable by life as we understand it. We call that habitability. Sounds like something Martha Stewart would talk about rooms. Feng Shui came up a few times, but habitability is more important. And that's what we've been doing now, and I'm not going to talk about that here, although I would dearly love to. Day 1860-something, on Mars, driving a lab through the hills. Great. But we went through that, and we realized there's other places that might be a better test of that extant life system without all the complications of the big, ancient, dusty Mars environment. And Europa is the first one. And so since then, we've stepped back and said, let's do the recon at Europa, cleverly, creatively, with the best of the tools without going there to prepare the way for what I'll talk about, a landed laboratory. And meanwhile, let's hopefully, as Thomas Zurbuchen recently said, bring back the samples of Mars to let all of you have at it. So let's look at the history of where we were. This is very simplified. Please don't shoot the messenger, but I wanted to say. So a long time ago, we had the tree of life. And we described a couple of kingdoms, and everything was grand. There's plants, there's animals, we're all good. There's a bunch of microbes, we kill them, it's fine. And there it is. And there's fish and swimmy things. And there's a mammoth. Oh, aren't they cute? So it was grand. We found the rock record. Dinosaurs were found. I even saw a trilobite digested in the rocks on the cliffs of Newport, Rhode Island. You know, amazing that you could survive those creatures in such igneous. So anyway, we discovered DNA, Watson and Crick and their team. And we sent the Viking probes to Mars. And they worked. The confidence of Voyager and Apollo gave us Viking. Notice we got the flag right, even though it wouldn't look like that if you landed, just to tell you. And we found that Mars was not cooperative. And meanwhile, biology went on. We discovered new limits of life, microbial, the deep sea, the so-called smokers. We discovered new kingdoms. Biology sequenced, invented the polymerase chain reaction method, CRISPR, all those great things came about. We had the Mars rock in '96, astrobiology was born, etc. And a new revolution occurred. We can sequence ourselves in anything, viruses, and we have a new tree of life. Carl Sagan would be proud, as would many biologists, because it's more complicated, it's more interesting, it reflects more on the history of what we define as life, and that leads us now to where we are. We were asked as a team to imagine searching for signs of the record of extant life in the European system against what we know about that system on the surface as part of a vision for looking at ocean worlds here and then later out there, astrophysically, if we can detect them. Now, we haven't been just sitting around. It's good to know. We've discovered organic molecules on Mars. The SAM instrument, a GCMS, tunable laser spectrometer, and gas chromatograph system that's on the surface of Mars now for day 1860, has discovered organic molecules. Chlorobenzenes. This is revolutionary. The dead, stale Mars that we didn't get has a methane cycle, chlorobenzenes, perchlorates, all this incredible chemistry. And the wheels are ripping away too as we drive. But it's not the life sign we were hoping for. It's not high up that ladder of life that I showed you. And meanwhile, we're getting ready to bring back potential organic molecules from the asteroid Bennu, a potentially hazardous asteroid, with the mission known as OSIRIS-REx, that is operated by University of Arizona, Lockheed Martin, and Goddard, with a team across the world that may get a chance to look in these building block molecules for signs of organics, maybe destroyed by space weathering. So today, we've set the clock going. But what's left is this magic of the ocean worlds. We like ocean worlds, right? How many of you have boats and like to go out on the water? No one. Okay. Oh, good. Just I got nervous. I thought we were an ocean-faring species. But the ocean worlds bring together one of the ingredients that we think is part of habitability. And now that we've discovered ones like Europa, mind you, there's no fish yet that we've discovered. But we can go back to this cycle that we first used in a paradigm published in 2000 when we restructured the Mars program, of using the reconnaissance we have from orbiting missions and even from our great telescopes to pave the way for in situ measurements by, in this case, a laboratory, and eventually resolve samples. This cycle has worked at Mars brilliantly for the last 20 years, and we've been executing on it. But ocean worlds are trickier. So let's look at what's the big deal. So, ocean worlds, let's find them. What do we know at the surface scale that you would stand on? Well, little asteroids, probably not ocean worlds. They didn't have enough mass to retain their volatiles, and so they chemically evolved differently. Nonetheless significant and important. The moon, it has a water cycle. We know that. Brilliant, no oceans. Too small, didn't get there. If it had them, they're gone. No record of them. Venus, probably a former ocean world if the models are right, but the big upheaval, it's gone. Maybe 1 billion years ago. Our own planet, of course, an ocean world. Mars, we think might have been a frozen ocean world with cycles of large frozen ice sheets that occasionally become ready to be more interesting. And then, of course, the Titan ocean world system around Saturn. And then there's Europa. Of these, the most potentially accessible, with the most communication of the ocean to the surface, is Europa. And so this nice little artist diagram is the rogues gallery of potential ocean worlds. You notice our own home planet, the big Galilean satellites here, Ganymede, Callisto, Europa, well, no, Io, and then the big dwarf planet Ceres in the asteroid belt, and Pluto and Mimas at Saturn, well, Pluto is its own world, and Triton at Neptune. So this is new, folks. 5, 6 years ago, belief that this is the case did not exist. So let's focus on Europa for a minute. So what makes Europa special? More water, more accessible, more probability of a dynamic world exchanging stuff. That's what we think. So the first thing is, the numbers we can all quibble about. But that Europa likely has an extremely large volume of liquid Newtonian fluids circulating under a thin ice shell is not in question. How much, how deep, where it's pocketed, how it varies, we don't know. And we can test that with a mission known as CLIPPER. And the structure we have then imagines this kind of architecture. Oceans, crack systems, diapirs, areas where that water erupts or exchanges with the exosphere so that we can have deposits of the good stuff, even if its survival of those molecules we want wouldn't last for a long time. Have any of you been to a deep smoker site in the East Pacific Rise, or anyone been down to see those? They're amazing because the damage post the eruption of the stuff you knew was alive means the signal you're trying to study is gone even here on Earth. So that's what we're up against at Europa. The exciting stuff has a short resonance time of measurement for what we're after. So this diagram done by Paul Mahaffey and team, I think, says it all. And I'm going to go through every molecule now so we can all, just kidding. But some of these molecules and what happens to them as a function of depth, pressure, and location inside this ocean shell on Europa is really what it's all about. Can we detect them? Some of these are alcohols, ethanes. You can read some of the organic molecules. The problem is as they get up into this radiation zone at the surface, where hundreds of millions of electron volts of radiation are pounding them in a cycle with the Jovian magnetic radiation belts, we destroy the signature of those. Experiments done at APL, at JPL in Europe show those large organic molecules become fragments that can't be detected as biologic if they're processed in the wrong way. So we need to get to the good stuff in the right place. And that makes the mission more tricky because to find where to go on something the size of Africa to get to the right stuff requires recon, positioning, and we're talking about a place that's a long way away. Now today we can land on Mars within about 10 kilometers of something. That's exceptional, okay? Probably within 3 or 5 as we get ready for the sample return mission of the 20s. 3 to 5 kilometers. The good stuff in Europa may be within a kilometer. And if we land a static vehicle that doesn't move, and we only have a few weeks to do our work, which is basically the defining conditions, what do? We need a better story. So we use the reconnaissance from a multi-flyby mission that doesn't have to live in those radiation belts every week, and to basically do the reconnaissance of Europa. That mission called CLIPPER is scheduled for launch in 22-23 with a bristling array of 12 experiments, brilliant ones, that will do the pathfinding. There's other things we could do that have been proposed, small fly-throughs that would do the reconnaissance of these potential vents, and then there's a landed lab. The bottom line is Europa has all the right stuff. So we ought to go look. We're questioning individuals. The first thing we can do, I see Mark in the front, is actually use astrophysics to help us. Now, I know that's heretical, Mark, but with the power of astrophysical spectroscopy in our solar system, we can do things that we planetary scientists don't often get to do. Ironically, I used the power of Hubble to detect titanium oxides on the moon as an experiment for the Vision for Space Exploration. Yes, Ed Weiler's still mad at me for doing that, but we actually proved we could do better than orbiters we have at the moon with Hubble. Now imagine the scale of sensitivity to these emanations of Europa from the power of the James Webb Telescope. And the value of it is its spectral power, its spato, is small enough that we could resolve the chemistries of small pockets of areas where these things could be coming from and watch their time variability. This is one of the experiments that's being discussed by the James Webb team, the solar system team, could allow us in the mid-IR to detect some species that would be very fruitful and may help point the CLIPPER to do the work we want to do. CLIPPER then comes along, and notice the size of this beast. It's a solar flyby orbiter that is going to the Jovian system, requiring a launch vehicle of the class we used to send human beings to the moon. So just think of that. We have not had that class of launch for robotic spacecraft in a generation. We're now going to go back to launch 12 to 15 metric tons, of which a couple will get into orbit around Jupiter and pass by Europa 40 to 50 times, depending on the tour. But this will paint the story of the world of Europa at the level that we need to plan a landed laboratory. Now, a lot of scientists ask, and you can ask me, and I won't have a complete answer. So why don't we just do that? Isn't that good enough? Why do we have to land? You know, orbiting is neat, but landing is slicker, I would say. Kind of a quote. Landing is slicker because we can bring the laboratories that are now so precise to the places where we can ask the questions, if we can get them there. We did that at Viking. We've done that on Mars. We're ready for Europa. So these big questions, and I won't read them all to you, about the structure of the planet, the deposits on the surface, the local scale geology that we'd have to land on, can be addressed by Clipper. That mission will launch, get there in the mid-20s, and map away. Hopefully last a lot longer than the plans. Clipper is the bridge, then, through its reconnaissance to find the places we can go. This is a map of Europa showing the regions at different resolution so that we could pick landing spots precise enough to send this absolutely perishable, brilliant lander to the right place. And so you see the areas in blue. There are areas where the resolution is about the scale we have now for global Mars. Some of you may be familiar with that. The areas in green are fine enough to resolve hazards that could impale small landed spacecraft. This is something the Clipper mission can give us through a camera system and developed at the Applied Physics Lab as well as other instruments. Now, you might say, well, why do we care? Well, we care because this is what the Europa we see today. Best resolution 30 feet, meaning you can resolve things about 50 feet. That's across this room. If you have a lander the size of 2 chairs and you're worried about things the size of this room, you might miss something that could be rather crushing on landing. And we can't predict the geology at that scale on Europa because it's not like the kind of silicate-based geology we've seen on the moon and Mars. We don't have that predictive tool. So there's Europa, and these are just areas on the Earth at different scales. Our Earth Observing System, MODIS, pictures just showing a glacier, areas from Landsat, and some of the views from the sub-meter resolution imagers, the Digital Globe Worldview, now called Maxar, I've been told, from the acquisition by McDonnell Detweller. But this change in scale is the scale we have to land on. So Clipper will give us that. And that then ushers in this next part of my talk. So the question put to us was, if you could land on Europa to carry out in situ science all about seeking signs of life as we understand it, what would you do? Is there a basis for doing that? Is it crazy? Are we ready? Do we understand biology enough? Do we have tools good enough to? This artist rendering of the tabletop-sized lander, US flag, NASA, is the early vision. Now, Thomas Edison once said, or he was quoted to have said, vision without execution is hallucination. So we dearly hope this is not that, but this is what we got. If we launch 12 to 15 metric tons of stuff from Earth, we can get about 300 to the surface of Europa in the place we want. 15,300. That's the lever arm to go to where you want to go in Europa. Imagine if you went on a vacation and you had that. Just think of what you take with you. All right. So our team worked for a year and came up with 3 central ways of asking the question. The whole issue of biosignatures. What is a forensic clue to something having been living? The question of environments recorded in the records of what we measure and the local dynamics. And the big kahuna here is life. And so we compartmentalized those questions with a large team into 4 areas that we felt would be fertile in a mission that probably would only have power to operate for a few weeks. And you might say, well, hold it, take more power. Well, first, it's a cold, very high radiation environment. Just getting the power there is a problem. Keeping the power conditioned so you can do work is a problem. The engineers, trust me, have worked out the trades. A few weeks on the surface with the right stuff is probably the right sweet spot. So there's the chemistry of that, the molecular biosignatures. the things that have the appearance of structure biology, the inorganic indicators that support those, and where the things came from. And I'm not going to go through all those. You can read the report. There's a nice 260-page science definition team report. Please read it. It's available for free. It's been peer-reviewed. We're pretty proud of it as a thought document. But some of the things we can now look at that we didn't know would be worth looking at since we last looked at this is microscale textures at tens of nanometers, where we start to see the kind of patterns that are not naturally inorganic. We have those calibrated based on things that we've now recognized from Earth environments that give us telltales for life. So here you see micron scale materials from recent papers about life from these deep accretionary lakes under the Antarctic, Lake Vostok. You see the work that my co-chair Allison Murray has done based on living things in the brines of Lake Vida and the dry valleys. How many of you here have been to the dry valleys in the Antarctic? Anyone? I recommend it if you can't go. But basically, these are some of the Earth clues to things that we didn't know existed. And so new capabilities, such as the microscopic capabilities we now have in labs, sent to Europa, could change the game. We have not taken a microscope, NASA, into space to date. We had plans for one on the Kraft Cassini mission. That part of that mission was canceled. We have a hand lens imager on Mars, but we have not taken things that can see the submicron scale, except for the atomic force microscope on Phoenix, which was an experiment, not was a technology demo, not a science experiment. But this is what life at that very small scale could look like in the kinds of environments. These tools now exist, staining, spectroscopic microscopes that we can test at the limits of life here on Earth. And so the astrobiology community has actually been looking at this question in earnest. They've looked at some of the signatures in places that we would not expect life. This is just not for scale. I think one of the most interesting ones is Lake Vostok, where we've used that as kind of a guide. We can't see a few cells as detected in a liter of water from Lake Vostok and their fragments on Europa, then we can't say definitively we've seen life. As Sagan said, quite profoundly, extraordinary claims require extraordinary evidence. So we have to do this right. Some of the salty lakes and the dry valleys also have incredible life systems. Lake Vida, Don Juan Pond. These are now the sort of the Europa experiences we have other than chambers. And just an example from a recent paper showing the brine veins where these halophiles have been discovered. So, life, Europa. We have to get to the right place. We have to have the tools to ask the right question. We have to do it safely. We have to communicate with Earth, a tall tale. And we have to put it into the context of this is what the Europa we know looks like. Chemically interesting. Mineralogically, perhaps responding to radiation and the chemistry of the ocean. And the context of a planet that might be rocking and rolling every 3.5 days underfoot. So that world that we go to is really a feed forward for exploration of any ocean world. Enceladus, Titan, potentially Triton, back to Pluto, still a planet to some. So this is our bullseye, if you will, ring diagram of the way a landed mission might be constructed to ask questions about potential signs of life in the context of environments and the dynamic geology. We took the challenge as a team, and this is going to give you a what if. If you had this architecture and it was technically feasible, what could you send that would address these questions? And I'm not going to go through all the nuances of instruments, but these kinds of instruments, which we have now flying on Mars, other places too, in orbit around Mars, at Jupiter, cameras, geophones, which are seismometers without all the 3D capability. These things address the kind of questions that we posed. We have existence proofs for them. We can figure out how much they should mass, how much energy they would need. If we were to compete things like these, given this bullseye, I have confidence the community of scientists would bid dozens of them, and we would have best pickings we can get. One of the things that's very important about thinking about Europa is the sense of scales. We're used to this scale. The scale we will get as we map the planet from reconnaissance flybys. Okay, the scale from basically few meters to kilometers. We're going to have that or experienced with it for the icy worlds. We're going to go down to sub-meter scale as we land, using the data from precision landing to help inform the site we land on. It's potentially we will have three-dimensional maps at centimeter scale of where we land to allow understanding of context. And then we get to the local scale where we can see sub-centimeter, and finally going for the first time to submicron, where biology gets interesting. Cell structures occur, as many of you know, at scales finer than a micron. We have not even measured submicron lunar dust completely. So what would the spacecraft look like if we could build it? So here's a regular-sized hominin kneeling, not praying, I've been told, next to the candidate vehicle. It is, if you choose for her to be doing that, that's fine. The class of vehicle we would stand. One of the things we realized we would need, and the engineers at the Jet Propulsion Lab and APL realized we probably need to land this kind of like a cricket would land when it bounces off your fireplace, in a wintertime. We have to be able to respond to an environment that we might not have the local scale. So these aren't legs. These are stabilizers. They're cricket legs. So this lander is affectionately known as the Cricket. This is an armed scoop system, not unlike that which we flew to Mars. This is the high-gain antenna with stereoscopic imagers that will give us the 3D imaging and instruments inside a vault. The reason we put the instruments inside a vault, you might say, well, they're protected. We're going to not let them get stolen. Those Europans, Arthur C. Clarke was worried about the Europans. Doubt they're going to steal our stuff, but if you've read 2010, please. But because of the environment is really not good for the electronics of gas chromatographs and Raman spectrometers and microscopes, and most of them don't really enjoy 10 to 200 million electron volts as a dosing constantly, and so we need to protect them. So this is the kind of first wave architecture of what it would take to put a landed vehicle on Europa with some really powerful science gear that would allow up to 5 samples to be interrogated through a whole chain of questions, and also ensuring planetary protection. Now, the other problem is we don't know what the local surface of Europa is going to look like. It could be pretty foreboding. So Earth glaciers, pretty rough. Wouldn't want to land on one. This is one of the best pictures of Europa from the Galileo solid-state imager. Devil's Golf Course at certain scales in Death Valley. How many of you have been there? Just wondering. Someone? Good. Really cool place. At the scale you walk over, you don't want to get lost there. It's a kind of precipitate environment and extremely tough. And, of course, the penitentes and other things that we know and love. These are realistic places that Europa could present. And this is the kind of architecture for landing we're going to need to have, combined with precision positioning. So this mission, if it were to fly, it's a concept now, has to land in the right place precisely, avoid obstacles, operate in an incredibly hard environment, sampling materials up to maybe 5 times through the chain of equipment of the quality we have on Mars today, and we'll be flying to Mars in 2020. Now, that's a lot of words I just gave, folks. Let's just parse that for a minute. That's everything we can do today at a world now a few hundred million miles farther than Mars, in a worse environment with different temperature regimes. That's what we're talking about doing as we search for life. So our strategy then is to seek life now in the records using a combination of reconnaissance scales, telescopic, flyby orbiting, and lander to get at this big Europa. Now that's a first step. But a lot of us in the community feel that ocean worlds are going to be a gift that keeps giving. We're not going to go to one because, how many of you have been to the Aral Sea? I ask these questions not just to inspire comment. Well, I was there. It did exist. Now I would argue it's probably not a sea. It's a rather interesting set of chemicals as an inland sea. If you want to go, please do. But the first ocean world lander that carries with it these kind of instruments will inspire the dreams of what could come. So here's Europa and all the places we want to go. The first orbiting spacecraft or flyby, the Clipper, will go in the 20s. We hope that a landing spacecraft carrying these biological assay equipment and geological tools will go to follow up at the local scale. Then a walking rover is conceivable, and some of us think that would be great. Others want the sample return, rather hard cryogenically. And then we have the submarine vehicles. Soft robots have been talked about for those of you that like that technology. But I come back to this cycle. So we can do these steps at Europa. And then the next steps will depend on what we learn. For Mars, we've come through this cycle. We've come through multiple seeks. We've gone to the surface, caching samples in 2020, testing molecular biosignatures to get ready for this. Where will this cycle take us in the ocean worlds is really the question. Do we leave it to competitive programs or we just do it? A lot of us feel we have to just do it. Now, there's other worthy ocean world targets. You know, when I was in grad school, we flew by this cute little moon of Saturn that we all called Enceladus. Enceladus is its name. We were all hungry as grad students, so we had to think lunch as we got the Voyager data back. But Enceladus has been shown, thanks to this legacy of Cassini, 17 years in Saturn orbit, to literally be erupting geysers of volatile species, including things that could also hearken to an oceanic system. And then there's the dwarf planet that was or wasn't, that shows us dynamics 39 AU from the sun are just as cool as they are on Earth. And who would have thunk? I mean, Alan got it right. This is another gift to us about the uniqueness of our solar system. And getting out there, not easy, worthy as well. But the first ocean world mission has to tackle that tying the knot from telescopic to reconnaissance to surface, so we have the training experience to know what we're at. We study Mars today because of training sites we've developed on Earth to understand that. So we need to do that at Europa. So let me finish with coming back to what you probably heard a few months ago from Mark and team. This baby, looks like Battlestar went astrophysical, has been on the boards literally for 20 years. It's taken 20 years to do Apollo without the astronauts for astrophysics. I mean, I think that's pretty good, right? I mean, I think so. I don't know. Maybe I'm patient. But this beast is not only a small increment better than Hubble. It's in a new wavelength, in a new place, with new potential, even in our solar system. And this aperture product power improvement allows spectroscopy that's exquisite. And of course, it's way cool. I mean, you know, here's a big dude next to it. You know, I mean, you could sit on this, although you wouldn't want to, Mark, sorry. No offense meant. But as you've probably heard from Aki and others, the rogues gallery of what might be the typical exoplanet, with an atmosphere at least, is increasing. Transiting exoplanetary surveys with spectroscopy are growing. Mark and team told you about those. That rogues gallery may show us our solar system's not ordinary, and that trying to follow the threads to understand exo-ocean worlds, EOWs, to NASA. No, I made that up. Could be, sorry, the temptation was too high. Is really important, but to understand what we get spectroscopically as we start to look beyond just the upper atmospheres that we can sense with a Webb, with a W first, and get into the deeper sense of what's at the surface solid interface, or whatever interface there is, it's going to take calibration with ocean worlds here. So we know what to expect. We need some understanding basis to predict so we know what to see. So our telescopes, designed for astrophysical problems through decadal surveys, brilliant, 27 years, test soon. It looks really cool now in development. James Webb, and of course coming up to one with a great French name, Levoir, who couldn't like Levoir, as we go beyond Webb, will all be triggered by what we learn out there and here. So we'll be inspired by the ocean worlds in our solar system that we're discovering now in planetary science to look beyond and to go to a scale here where we can understand things about them. And potentially to look at the spectral record of what those worlds look like, calibrated against what we see in plumes from Europa, Enceladus, leaks that could occur at Pluto from fresh deposits. These signatures, these fingerprints, are detectable. They're detectable in our solar system with assets that we'll be flying in the next few years. They're detectable when we fly by. And they're detectable beyond at least to certain limits around certain kinds of stars with the techniques we're developing now. So let me conclude with two thoughts. The first thought is, this is a tough question, and we all care. I mean, there's life in us that may be killing us, but you know, what the heck, we live with it. And it's the magic ingredient that makes us special here on our life-bearing world. And how we extend life, you know, is a key question as NASA goes forward. We're looking for the ancient signs of life in lots of places. Mars, potentially other worlds, asteroids in the record. But the first place to look for living evidence that exists today that might be communicating with space is potentially Europa. It may be hard, but it's a worthy cause from the eyes of our science definition team. And then beyond those exo-ocean worlds, those planets with the methane-oxygen mixing ratios that are exciting for life, that aren't easily made geologically, if we really understand that, beckon as well. So we're ready to go. We have the vision. We don't think we're hallucinating. We haven't in the past. We may have thought that after Viking came back with its results, but I would submit we haven't. So we're ready to take this leap across the dimension, and it all feeds back here to the limits of life on Earth and our own survival. And who would have thought that, the sarcophagus of Chernobyl is brimming with all kinds of interesting things. Lord knows what they are, but some of you may have thought about it. I'm not going in there, but some of the microbiologists may. But this connection really connects us to the universe and the solar system. And as we go back to places like this and bring our biology to those environments, someday, I'm not saying we're going to Europa. I know Arthur C. wanted people, but at least there, we can start to imagine what happens to that space impression on life as we understand it. And we do that in space station. So I leave you with the thought, Europa is a special place. It's presented itself to us over a generation. I think we're ready to go. Landing on Europa could be one of those literally paradigm-busting opportunities for us. Some of you young folks here, I hope, will see it. We can do it, the team of folks, and we're ready. So I'll stop there and take questions.
So we have time for questions. We have a procedure, and that is you have to raise your hand and keep it up long enough for somebody with a microphone to spot you. They will bring you the microphone, and I'll point at you, and then you can ask a question. So we have an eager hand over there.
Eager hand over there.
And he
Yes,
gets
sir.
the microphone. And tell us your name and whether you're a member.
My name is Jerry Gallucci.
Are you a member?
Not yet.
Sign him up, Larry.
No, there's no penalty.
Okay.
But give up the microphone now.
Jeez, you scared me.
Okay. It seems that your search for life on Enceladus is based upon the notion that it's carbon-based, perhaps, or it's something like us. Wouldn't it also be an obvious thing to look at Titan? Because that has a visible cycle of oceans and weather and rain or whatever. The chemistry might be different, but why not Titan, where you don't have to bury through ice?
So the question, if those of you didn't hear, was, I'll get to you in a second. So there is no perfect ocean world target. You're right. There's lots of them. I showed you a half dozen, all with different engineering science challenges. And Titan is a totally worthy object that some colleagues feel, I'm just speaking for the community, that can be accessed through competitive programs. Missions have been bid that could have gone to Titan and asked some of those questions. And so the chemistry at Titan may be willing to show another sign of how life works. Titan offers a deeper look back in time of one of these primeval atmospheres that we think is very important relative to Earth. Europa offers the communication of, we think, a briny liquid ocean with a surface in a different state. And so as a working idea, the idea of getting there first, following the legacy of the Clipper mission to paint the habitability prospects is the working condition. Quite frankly, it could be any of them. Europa is closer and will have better recon from the standpoint of what Clipper will do with an amazing array of instruments than any other place. So following that seek in situ cycle paradigm that we developed in 2000 and presented to the Academy in many places, Europa would be a good target. But Titan's great. Enceladus, or Enceladus if you prefer, is also fantastic. And there are even mission proposals to land and flop around on Titan, fly through the plumes of Enceladus with in situ flypaper-like instruments, electrophoresis. These are fantastic. And the way we do science, thanks to Thomas Zurbuchen and others, is to have some core programs that develop a capability for a future as strategic things. Scientists propose the instruments to go with the vehicles, and others completely competed at the mission level. Pick your poison. Fly a boat to Titan, as my friend Ellen Stofan did, and could have flown. So it's just a question. Just like on Mars, why don't we just go to the polar caps? They're pretty cool, and they are. But there's lots of ways to look at the question. So you're right. I'm just saying there is some momentum toward Europa because of the modern cycle of potential biology that makes it very attractive. But the earlier cycle that could be presented at Titan is also magnificent, and Cassini's shown us that. Does that help? I'm sorry, it wasn't a complete answer. Yes, Larry, sir.
Other more questions?
There were hands up, gentlemen
Barry.
here.
Carrie Liss, APL.
Yep,
So, very interesting talk. You've described a static lander in one place on Europa.
right.
Have you considered, instead of a focused lander in one place, a rover with less focus but go to many places? Or conversely, let's say you do the lander. Where would you pick the best place you think to find that life? Right near a vent that spat out stuff from underneath? Because on the surface we think it's dead because of the radiation. So if you could comment on those.
Okay, so the first question is, roving is definitely incredibly attractive. It was a decision made for Mars against great churn, I might add, in 2000 when that case was made. The problem is, for the first one, with the kind of payload and the kind of mass delivery and the kind of challenges for, what should I say, environmental access and motility, and the power available to move for a short period of time, you start to stack those up, and all of a sudden, a landed mission is as expensive as the James Webb Space Telescope. And you have to ask, given what science is being fed by James Webb across astrophysics and solar system versus the crawler on Europa, if that's the right approach. But your second question is a great one. So where do you go? Now let's, for a minute, folks, and I probably went over this too quickly and I apologize. We're talking about pinpoint landing on Europa. That has never been done by humanity except on the moon, just for scale. Apollo 12, 100 meters from Surveyor, pretty dang good for 1969. So we haven't done that. We land miles from things and hundreds of miles from things. So now, your point, if we found a fresh deposit that was spewing away, like my new little volcano in the Southwest Pacific, hint, hint, Hunga Tonga, was erupting beautifully 2 years ago, produced fresh deposits of fragile minerals. They're already gone in 2 years on Earth. So the radiation damage on Europa is a real concern. So how do we find the places to go? Clipper will give us the basis for making that decision. We don't have it today. If Webb saw active plumes filled with interesting molecules, we could at least localize, probably to 100 kilometers, 50 kilometers. So that's the key question. In the report, we described a triage system of establishing some safe but useful landing sites that would escape instant radiation destruction of all complicated organics and cells. One piece of evidence, though, extreme radiation damage of cell walls is partly contained in some of the presumed mineralogies that would be on the European surface. And so some of the astrobiologists are convinced you could preserve fragments of cell walls if you can look for them with microscopes. So we might still, even in bad places, be able to get something. Yeah.
Yep, stand up.
Is the flexure worse at the actual crevices? Is
So-
that a counter argument? Pardon me.
So the question is, we have this big Europa with this churning ocean and this 3.5-day cycle, and our best educated guesses from geophysics suggest a 3 to 30 meter global oscillation of that crust responding to that stress of the ocean and the tidal pull of Jupiter, quite frankly. Where would that be localized? Well, crack tip propagation, good old solid mechanics, little something to the fourth power. It's going to be preferentially focused at areas of weakness. Thinner crust with cracks will get more action. And that's solid mechanics. And so we think that would be a place to go, but that might be a tougher place to handle. And so one of the things on the mission we've talked about is doing 3D surveys, Alex Hayes actually at APL, of the region where we land to look for motions propagated at small scales in the period of time we're there to measure that. So very good question. Question in the back, I see you might, there, gentlemen.
Joseph Powers.
Hi, Joe.
I just wondered, at more than 5 AU away, you're at less than 4% of the solar flux around Earth. So why waste any of your mass budget on solar panels? Why not just nuke up with RTGs or an actual
nuke up.
Reactor?
I like the
let's
nuke
be
up.
realistic here.
Get that down.
It's
Mark?
less than 4% of the sunlight that you get on a sunny day.
So Joe, I neglected to go into all the engineering details. The landed mission is battery powered. It has a total power budget of 45 kilowatt hours, plus or minus 5, to expend however you want. You can dribble it across a year or use it up in 3 weeks, depending on comm cycles, drilling cycles or digging, whatever, cycles, and processing instruments through temperature changes that you would use. So that's the easiest way to do a mission of this sort, carrying an MMRTG with the planetary protection constraints of a world that might contain current extant biology. I'm imagining the paperwork might be like this, maybe worse. Just launching Cassini had its challenges, and landing MSL Curiosity. So good point. JPL and other colleagues, actually colleagues from APL, have looked at the trades, put a small MMRTG. Now we actually don't have fuel for all of them, minor detail, but still. So the battery-powered solution gives us enough time to process enough samples, fast enough, with a comm loop, to actually do the mission defined by the SDT. Now, would you like a bigger mission? Sure. But that's good enough to address the first order question. Is there the biological evidence through those lines of reasoning I showed? And I didn't want to show the whole trace matrix because you wouldn't be able to read it because it's pages long.
I mean,
but
there's plenty of strontium-90 that's baked into strontium-titanate. There's one
Understood.
RTG that survived a rocket that blew up in midair.
Understood.
It was reused.
Right.
So, I mean,
The question
you're
comes
expecting
down-
this life to live off the heat of the tide from Jupiter. So, it's a hot rock. There's plenty of hot rocks there. I just don't get it.
So your point is a good one. However, the other factor is the spacecraft sitting there in 10 to 200 million electron volt environments will be degrading constantly. The data from the JunoCam that has flown 8 times in a perijove on Juno has already shown a 45% degradation to the CTD, a CMOS thing, in just 8 dips. 8 dips, in and out, 45. So, that's minutes in and out. So keeping this thing alive, functioning as a spacecraft that can send back information in this environment, unless we bury it, but burying in a place where we don't have the civil engineering knowledge of the environments, I mean, as we said I have to just tell one story. We asked the naval reactors guys that built reactors for us here in the United States, out in western Pennsylvania, so what would it take to put a big reactor on Mars? And they said, 20 years of civil engineering studies of, heat transmission in the material and blah, 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 just to do it safely. And so, these are not trivial issues. I agree with you. An MMRTG-powered lander would be great. Of course, it would weigh more, have different launch issues. But we can do the science that this team put forth and had reviewed with a battery-powered lander, with an orbiter that supports comm. So, other questions? Good question. I don't know. Whoever's next.
Bob, go ahead.
This gentleman, or there was a gentleman back there, and way in the back waving his hand.
Yeah.
Oh, okay, that gentleman. Yes.
Hi, Michael Clifford. So we just tossed Cassini. Can you hear me?
Yeah, I think.
Hello?
There, good.
Good, that's better. So we just tossed Cassini into Jupiter to prevent it from crashing into one of the moons and contaminating them and messing up life over there. But if we want to land on one of these moons, we're going to be contaminating the moon. So how do you get around that?
So the question is a great one. So we're going to land on Europa. Now, Europa is kind of sterilizing itself because it's in the Jovian radiation belts, which are kind of sterilizing of anything we understand, as the point made by another colleague. So we will use biobarrier systems, which have standards of cell counts, microbial loads, and use a dry heat sterilization method on anything that would have contact with the surface. But just flying in the radiation belts alone meets the current planetary protection standards for sterilization just getting there. So we would still do more. Because again, we're not looking for the little swimming fish, which would be great, by the way. I wouldn't eat it. We're looking for the forensic evidence of that biological processing, however it's preserved. Because if we say we're looking directly for life, which is a great thing to do, we have to avoid what people thought happened with Viking, that we went in hot and got it wrong. Not that we weren't smart, because we were, but we didn't know enough about the boundary conditions of the physics and chemistry. So your point's good. We have to be careful not to bring the life with us. Remember what happened on Curiosity when the first run through the SAM instrument happened. We measured the Florida air that we brought with us to Mars. We cleaned it out and realized what was left was Mars. And Paul and his team across the country did that. So we will have to be careful, and that's a great point. And we do take that very seriously at NASA and across the community of people who would be interested in this mission. So excellent question.
Bob.
Yeah, there was another, oh, Bob.
Bob Hershey, I'm a member. How about these others that you had mentioned, of Enceladus and Pluto and Titan? Would those be in parallel maybe every few years, or are you going to wait for all the results from Europa?
So, great question. Let's scatter these landed laboratories across the solar system. And Bob, that's a great idea. These things are challenging developments, and they cost money. And, so the way presently NASA works, which I think is good, you can argue, is we have competed programs up to a certain limit. The biggest are called New Frontiers. Several bids to do ocean world exploration were submitted by major players to ocean worlds. I'm hoping one gets selected by the end of the year as for a big major study. So we can get to places in these openly competed programs, whole missions, with a single principal investigator, woman or man, and their team. We can also, so we can do that. We can trade with the community of advisors through decadals and other places. Is Europa the right answer? After we're putting all of our eggs, pardon that pun, in the Clipper mission to get to know it, because it's so compelling. And most of the community, although we'll all argue, because we love to, would say there is the potential of an amazing signal there that would connect to very modern processes. So, and it's a dynamic geologic world that could be one of the most topsy-turvy we've ever seen. So there's collateral benefits. So I think a multi-frontal exposure with competed missions every 4 to 6 years that could get there, and bigger ones that we call strategic, could balance that playing field. Planetary is different than astrophysics, where we need big observatories in unique places to produce the data for the community. We can go, or fly by, or land, or there's a lot of different vantage point potential. Use telescopes, for that matter. So it's a great question. They're all great. Trust me, I'm agnostic about that. Which can we get to first that opens the doors for all of them with the techniques that will let everyone play would be best, in my view. And so getting to Europa and making it work could allow smaller, less expensive ones to some of these other worlds based on that technology pathfinder. Does that make sense? Okay. So sorry if I am all European.
Rudy, question.
Yes.
Yes,
It's not a speech, question.
a question. My name's Rudy Krutar. I'm once and future member of the society. And when I was a child, Europa was the common market for many European countries. The question is Europa interested in Europa? Is there any marketing value in the coincidence of names?
So, great question. If I understand it, forgive me for slowness. The European Space Agency does have a mission to the Jovian system, very nicely named JUICE. It's focused on another particular object and touring several. We'll have some observations of Europa, which are exciting. It's a multi-flyby touring type mission. NASA has an investment in a big instrument on it, a type of radar, which I'm personally very fond of, but forget that comment. So there is that benefit. We would anticipate that if NASA goes forward, choices being made by senior officials, not me, goes forward with the Europa lander, at least to the next phase, that a competition for payloads would happen, and our friends in other spacefaring nations, Europe, Canada, Japan, around the world would participate. Russia, we would hope as well, potentially others. And so the science community, fortunately, are interested in this. They've reflected that in Europe and in the United States. I'm not sure Europa is linked to so much Europe as to naming conventions that go back to the Renaissance, but we can all wonder about that and debate it over potables. But nonetheless, it is an extremely attractive target. And just like the first good place to look for ancient signs of life may be Mars, we can debate that. Europa may be the first good place to have the systems to see expression of modern extant biology of some sort. Maybe not the kind we think, but again. So, other questions? I thought I saw one. Yes, sir.
Carl's next.
Carl's next. Okay, Carl. Yes, Carl.
Carl Merrill,
Yes, Carl.
member of the
Then you
society.
can go.
I was impressed by the shielding and hardening of the system for the satellite that went around Mercury. And so what you're saying is that the radiation here may be even greater than close to the sun. Is that correct?
It's different, Carl, in the sense of thermal versus electrons and other species. So we have radiation belts at Jupiter producing the large dosage at, and also tidal, at Europa. At Mercury, we have solar protons and thermal.
Right.
And so that solution that the Applied Physics Lab used for MESSENGER to shield the spacecraft and have a hot side, cold side thermal balance worked brilliantly, and that's actually a variant that's being used on the Parker Solar Probe, which we'll be launching next year.
But I was thinking about the solar wind with the protons there.
Right.
And the other thing was, didn't Hal say we should stay away from Europa?
Hal did. But remember, Hal was the sibling of IBM, and so IBM is now going quantum. So
That was
maybe,
HAL 2000.
Oh, that was HAL 2000. Yes, we have 2010 now, Carl, so we're beyond that. But good point. And there are technologies now that are emergent for Mercury, for solar, and radiation. There's even dynamic radiation shielding using mini magnetospheric inflation techniques that have been demonstrated at Marshall, where you can actually use a magnetic field to shield yourself from radiation. However, making them work the first time you go land, there's some details. But they have inflated a chamber with high radiation down in Huntsville that could actually shield some of the high energy electrons. Really kind of cool stuff.
Next question's over here.
Okay, we had a question over here, sir. Sorry.
Yeah, I just wanted to ask where all this radiation comes from on Jupiter.
Well, Jupiter is got a huge internal magnetohydrodynamo, basically like Earth. It generates a huge magnetic field. And from that and the chemistry of its atmosphere and its inner, I don't know what you want to call it, it's not a core, innermost region of metallic hydrogen and other species, it generates electrons and other species that produce a belt, just like the radiation belts we have interacting with the Earth from the sun. What we've been measuring. So we measured that radiation with Galileo, and we flew by it with Voyager, and we're measuring today with Juno, with a mission that's studying the deeper interior. And the Galileo probe also measured species. So we have a model, not perfect, that explains the radiation at Europa, and we actually have built laboratory simulations of that radiation environment. So we've gone through the characterizing, understanding, predicting state. Now, do we have it exactly right? What we see at Europa from the measurements we have from Galileo, limited because of the high gain antenna problem, does support the models. Now, Jupiter is spinning, has a very short rotation cycle, and that's generating a lot of energy, spinning up a lot of stuff that is interacting with these inner moons. So Io and Amalthea, Io, and Europa are particularly damaged by that. Does that make sense?
Okay, thank you.
If you want to know more,
I don't understand it yet, but I'll look into it.
you may want to come to the next lecture then, because it's about, maybe not Europa, but it's certainly about so-called space weather, which has a lot to do with radiation and ionic fields and magnetic fields. And
that's Auntie.
Yeah.
Come next time. Great speaker with some great stories, and he's actually tracking whales, which is also interesting if you're interested in that. So other questions? I saw one somewhere with a microphone was being raised, but maybe dropped. Nope.
Oh, yes, excellent.
Yes. Great. Oh, good, a question. Yes.
You can ask your question. Stand up. Say your name.
Hi.
My name is Sarah.
Pardon?
My name is Sarah.
Oh, hi, Sarah. I'm Jim. That's Larry. He's the boss.
Question.
Are you perfectly sure that there's water on that planet?
Very good question. Excellent question. So, thank you, Sarah. So, I've been standing up here, spewing forth lots of talk about water. How do we know? The first thing we know is we can see the reflection of light in stuff made mostly of water with other impurities really well. It's like a fingerprint. And we've done that ever since we first flew by Europa in 1979, before you were born. It's a long time ago, in a lost decade, apparently, I've been told. Sorry, that's what the 70s were. I don't know. Tom Petty, I think Tom Petty said that. Oh yeah, sorry, Mark. So, Sarah, secondly, we have measured, it's hard to explain this. Inside Europa, things are churning, and they generate kind of like a magnet. And we've measured that variation as we've flown by, and that tells us that there's probably sloshing large amounts of water, generating that fingerprint. And we think, but it can be debated, sorry, that with Hubble Space Telescope and other assets like that, we have detected some water-like stuff coming off Europa with big telescopes that can see a long way. You know, the Hubble Space Telescope is like a school bus, you know, like the Magic School Bus, but it has things on it. So we think we have 3 lines of evidence of water at least.
You also know Europa's density.
Right, and we can also, right, and he's right. The density of that object, if you can think of it as a big ball, if it were rock, it would have a density like Earth or Venus or Mercury, but it's less. It's less than our moon. So it means something inside it is squishier than the rocks we know on our moon and elsewhere. Now, there's lots of ways we would love to get down inside Europa with our submarines and take young people like her, or even soft robots. I would personally love those. But any other thoughts? Great question, Sarah. Thank you. Oh,
So maybe one more question?
One more question?
You have another question? Or
Yes.
There's one way in the back
way in
there.
the back. I
That'll
see a
be our
hand.
last question.
Nope. A hand or
Yeah, it's a hand.
Oh, good. Oh, up front. There's a guy
Oh,
waving
there's a guy
back there.
All right, we'll take
All right,
two.
well, we'll take two
You
because
got the microphone first, so you
someone
can go,
seems
and then
earnest.
the one in the back can go.
Hi, I was just wondering about the logistical challenges of landing on Europa. Would it have to be like a sky crane or like, because you said it had to be very precise, right?
So the way the working model is to adapt the propulsive entry system that we affectionately call the sky crane to Europa. And basically the way it would work is we would go into an orbit around Europa, painful, spiral down close enough where we can release this 800-pound system, of which 300 is the lander, with a sky crane-like device and a big, huge solid rocket motor. That solid rocket motor would burn for minutes to basically do the braking burn, to do what we call deorbit, descent, and landing. Now, all of you who know, sorry about this shop talk, know about landing on planets, we talk about EDL. It sounded like, you know, something I read in a popular magazine that I didn't want to read. But EDL is entry, descent, landing. So this would be deorbit, descent, and landing. That big rocket would be jettisoned, the spacecraft would rotate, and then winch down, fly to a spot using terrain relative navigation, active LiDAR, hazard avoidance. Fly to the point already mapped by Clipper with the camera system, ICE and others. Map to that, fly to the point, and land within, we think, tens of meters of it. That mathematically closes. We can do that. We've tested helicopters to do it. But there's a lot of devils in the details. And just for example, the LiDAR has to produce 4 megapixels a second of precision ranging data. Well, just for scale, the commercial industry in the US is about 1. So now we have to do 4 times that in seconds to know we're not going to land on the bad thing. We also have to collect images under weird lighting. We'll probably use structure from motion for those of you who like computer vision, which is really cool. So there's a lot of logistic stuff. And, you know, the alternative, and this gentleman asked really well, just land within 100 kilometers of something. But you got a few weeks. You want to be in the good stuff. There's plenty of not good stuff that would be great to measure. But you're taking a biological, type of analytical laboratory, you want to go to this stuff. We've been driving for 5 years on Mars to get to the good stuff. So we want to go to the good stuff. We think we can find the good stuff with Clipper. We are pretty confident with spectroscopy and imaging and other dust and mass spectrometry, we can do that. So we want to go there. We think we can do that. And that's one of the benefits of learning to do that on Mars and then feeding it forward. And then making that technology available to the community. Use it at Enceladus if you want. Or back to the moon. Does that make sense?
Yeah, definitely.
So it's a lot of stuff. This is not a mission for the faint of something. Heart. The other question was somewhere over there, sir.
Hi, Paul Hess, not yet a member. You talked about taking 5 samples. Are the plans to have diversity of collecting the samples or 5 repetitions?
Great question,
Type of quick
and
sample?
much debated for more than a year amongst the 20-odd colleagues. So it really is a function of what you would define as reproducibility of result. Should we get a positive result? And if we don't, how many more takes you would take somewhere else to do better, given that your sample area is probably this. So you land your little table and you have this 7-foot arm with a cutting tool and a scoop-like delivery system, and that's it. So the initial idea was to do a trench, at least 10 to 20 centimeters down. That has something to do with the skin depth of radiation penetration into certain minerals. The salty ones are different than the silicates and the pure ices. Get that sample back and do the recon quickly on that and decide, are we getting to stuff that's not as radiation damaged there through the chain of analytical measurements, or go somewhere else, or keep digging? And those questions, until we get more data from Clipper and better models, and even go there, we're not going to know. Now, at JPL, Kevin Hand has a Europa chamber. He can simulate thin-skinned effects under the radiation and temperature regime at Europa. And he's doing experiments. There's others being done, I think, at APL, at least computationally. And so we have a scheme. It looks like a subway map. It says, you dig once. If you get this, go there. If not, come back over here, go there. And 5 was the magic number in a mission with a cycle of 21 to 25 days. And that would allow 3 to constitute a reproducibility basis in biology, according to our biologists. But, if they're all dry, what do? I mean, and that's one of the challenges. Now, we also have to worry about the sky crane not blasting the landing zone. I don't know if you saw Curiosity came down, and there's this blemish of, 300 meters across where all the dust was blown away, and nice conglomerates, all good stuff. So we have to be very attentive to that and blow that propulsive maneuvering system away with canted engines, get the heck out of there so we don't contaminate the landing site for these precision measurements. There's a lot of details. However, most of us felt, I think all of us in this game felt it was worth the challenge because we're asking tough questions. And so Sarah can get to do this kind of thing again and again and again. And maybe she'll fly her own soft robot down into the oceans of Europa. So good question. There is a strategy. It's in the report.
Well, thank you.
Oh, thanks,
Come
Larry.
back there.
All right.
So thank you, Jim, and appreciation for coming down here and spending time with us and giving this fabulous lecture. I'm going to present you with this framed, signed copy of an announcement of your talk on behalf of the General Committee and all the membership.
Thank you, Larry.
Very much.
Really appreciate having me. Thank you, folks. I'll move over here.
Just go sit down.
All right.
Just go sit.
Oh, okay. Go sit.
Go sit.
Sorry. I don't know what I'm supposed to do.
Yeah, I want the stage to myself.
He wants the stage to himself.
So,
Okay.
Before we go, we have a few housekeeping items. First and foremost, thank you to all our members and guests and sponsors and supporters and our volunteers who make all this possible, our videographer, Noreen Clemency and Robert Clemency, and our new streaming person, Jared McQueen, especially. So just a word for them. Just remember, we just depend on our members to support the institution financially and make these lectures available to the public for free. So if you're not a member, please consider joining. And for those of you who are confused about how to join, it's pretty easy. You can go to this old website, which will shortly be replaced, so this information is time limited, so you better sign up soon. Anyway, you go to the current lectures at the top. You'll see down there it says membership. And if you click on membership, you'll get to an application for membership, believe it or not. And then if you go down to the bottom of that, it'll say submit. So we do ask you for some basic information. Hit the submit button, and you should get, whoops, oh dear. Well, I messed up. We don't have the screen. This is the screen after the screen I wanted to show you. You get a screen that has 2 buttons. One button is use PayPal, one button is use something else. Most people don't want to use PayPal. They're very confused by this. Just hit the use something else button, and then you'll get this, and you can just fill it out the way you would for any credit card payment on the web. So our next meeting is the 2,381st meeting. It will be in 2 weeks on 20 October, right here in the PAL. We're going to have a talk on space weather, earthly effects, sunspots, iron storms, magnetic shields, plasma wake fields. And it's by Antti Pulkkinen, and he's an astrophysicist and acting deputy director of the Heliophysics Division at NASA Goddard Space Flight Center and an adjunct professor of astrophysics at the Catholic University of America. Thereafter, we'll have a talk by Brian Cook of Amazon Web Services and a professor at University College London. He's going to talk about ensuring that software behaves. And for those of you who use Windows, you may have noticed that in recent iterations of that lovely program, you don't get the blue screen of death very often. And this is the guy who figured out how to make that not happen as much. Even though they said you couldn't predict the sort of errors that were occurring in the program, he came up with methods for predicting the unpredictable. Then we have a really interesting talk by Jerry Joyce, who's at Salk and Novartis, on Life 2.0. He's a guy who creates chemical systems that mimic life, at least. And in particular, he works on making RNA behave like proteins and DNA. And then we have a talk by Nima Arkani Hamad. And he's at Princeton at the Institute for Advanced Studies. He's figured in the film particle fever, which we might show again before this particular lecture. We did it for another speaker, David Kaplan, who actually made the film and is a friend of Nima's. So he's going to talk about some topic in physics, but he won't tell me what exactly. I'm hoping that it will tunnel through his barrier, and I'll soon know by quantum mechanical means. And then we have Doug Smith at long last, because I've been trying for a long time to get somebody to come and talk on metamaterials. And he's one of the leaders in the field, and it works with Sir John Pendry, who is probably the founder of this field and probably will win a Nobel Prize at some point. And he invented the cloaking device. For those of you who are interested in cell technology and watch Star Trek, well, there's actually possible to make something that actually works that way. So this should be very interesting, and I'm keeping the president's lecture a secret. But I think it's going to be on a woman from the Harvard MIT who works on sequencing single cells and is making the encyclopedia of cells based on nucleic acid analysis. Aviv Rashid is her name, and hopefully she can do it. So with that, I guess, what should I say? I don't know. I have to look at my notes. But I think it's good to keep in mind that the social hour ends at 10:30, and we have to leave the room at that time. But fear not, that's not the end of the evening. If you want to stay later, we will go across the street to the Fairfax Hotel Lounge, once known as the Jockey Club, and continue our discussion there. And I think with that, I'll take a motion to adjourn the meeting. Bob is handy member, always good for a motion to adjourn. Do we have a second? And all members in favor of adjournment? All opposed? Oh, I guess we'll have to adjourn. Meeting's adjourned.
This is, I think, yours, Larry?
Yeah.
I don't want to lose it. Thank you. I also have all this stuff here. That's a good quick question. Yeah.